I hope. Is it? Yes, it is. Okay. Yeah, so I was saying there are several ways of doing machine learning. And one of them, if you really want to understand the foundations of machine learning, you need a lot of math, okay? A lot of mathematics. And what are the hot topics in mathematics that are useful to machine learning? Of course, not every type of mathematics are useful. There are some domains that are more important than the others. Maybe um, I can also apply the so can you see the, yeah, okay. Okay, so a lot of math. The first domain, we are going to see this later, is optimization. Optimization. Okay, why do you need optimization in machine learning? Well, essentially, training a model requires to find some parameter values. Okay, you need to find some parameter values. Let's say alpha is the set of parameters. And actually, you want to find alpha in such a way that you minimize the error. Okay. Donc the subject in machine learning is find the optimal values of some parameters such that they minimize the error you produce. And that's the first domain. You need optimization. That's the main one. The second one is linear algebra. Linear algebra. Why do you need linear algebra? It's not only basic linear algebra. Okay, it's advanced linear algebra. Well, essentially because all the operations that are performed, for example, for neural networks and other type of things, are encoded using vector, matrices, and more generally tensors. Okay, so a tensor is a multilinear application working on linear spaces. We are going to see this later, but take that in mind. Linear algebra is an essential part of machine learning. And also because for dimensional reduction, you have a very important technique called the singular value decomposition, okay? And the principal component analysis. Okay, so that's the second domain we are going to study this year, linear algebra. The third one is probability. Okay, probability. Why do you need probability? Well, because all the machine learning, well, not all the machine learning algorithms, but almost all have a probabilistic interpretation. Okay. Do you see my screen? Yeah. Okay.
Yes, we do.
Yeah, yes.
Yes.
They have a probabilistic interpretation, and that means that um, you have some data. Okay, you have some data, and you have to measure your confidence on a certain prediction. Okay, let's say you see an image and you want to know if in that image you have an orange or you have a car or everything. Well, in that case, you need to evaluate the probability that in the image you have a car or an orange or whatever, knowing the fact that you have some experience, some data. Okay, so this is for the next year, but I'm trying to give you the motivation. So probability is very important, in particular something called Bayesian probability, okay, the Bayes rules. And we are going to talk a lot about the Bayes rules, okay. Optimization, linear algebra, probability, and of course, analysis, okay. In analysis, we're going to see how to compute derivatives of more complicated objects than just functions. Okay, we need analysis for the study of backpropagation algorithm for neural networks. We need also analysis for all the characterizations of the gradient descent, stochastic gradient descent, etc. Okay. Well, that's the motivation. So this course on mathematics is very, very important for you for the next year if you want to understand well the different concepts we are going to see next year. Okay, so that's the first branch of machine learning. If you want to really understand the foundations of the algorithms, you need a lot of math. And of course, there's another way of doing that. It's more the way they implement on other lectures, much more just use some libraries on scikit-learn or whatever and launch. It's more it's a less not rigorous, but well, it's a different type of doing machine learning. You need both, okay? But my responsibility is to teach you the foundations. Okay, so probability, okay? In probability, you have the basic language which is set theory, okay? Do anyone know how to say set in French? What's the translation of set?
C'est un jeu.
Ensemble.
C'est un ensemble, okay? So set theory, c'est la théorie des ensembles, okay? And in set theory, you have potatoes like this, okay? This potato is called the universe omega, okay? And the basic idea is that if you have a subset of omega, let's call it A, okay? So we say that A is a subset of omega. The probability of this event A, it's the measure or the size of A with respect to omega, okay? So if you compute probability of events, you want to know what's the size of the event with respect to the size of omega. So omega with respect to himself has size 1, okay? That's the reason that the probability of the universe omega is 1. Why? Because the size of omega with respect to omega is 1. It's 100% of the universe, okay? Now, if omega takes a smaller part, which is not the whole set omega, we can directly know that P of omega is a number between 0 and 1. A probability is always a number between 0 and 1. Okay? Why? Because it's always the measure of a subset with respect to the set omega. Okay, so this is very basic. You normally already don't know that. And the lecture we are going to study is much more difficult than that. Okay, but just to recall you some things. Okay, if you have a subset A and a subset B, so let A be subsets of omega. Okay, so this notation, it's very important for you to know. P of omega is the set of all the subsets of omega. It's called the power set. Power set of omega. And it is the set of all the subsets of omega. Okay, this is a definition. P of omega is the set of all the subsets of omega. Okay, so in French, c'est l'ensemble de parties, c'est-à-dire l'ensemble de tous les sous-ensembles de omega. So when I say A, B are in P of omega, I'm just saying that A and B are two subsets of omega. Okay, so omega is here, this is A, and B is somewhere there. Okay, A and B are subsets of omega. And from those subsets, you can construct another subset called the union, A union B. You can construct the intersection, A intersection with B. Okay, and those new sets can be defined in terms of the elements they contain. So, for example, A union B is the set of all the X such that X is in A or X is in B. And this OR is an inclusive OR. It's not the XOR, inclusive OR. That means that you can be, of course, on A and in B at the same time. Okay, it's not the OR as in the restaurant, which is exclusive. If you say you can take the entry and the main dish, or the main dish and the dessert, you can have both. Okay, but here in math, when we say OR, it's normally an inclusive OR. That means that we can have both. We can be in A, we can be in B, we can be in both. That means in the intersection. So the intersection is the set of X such that X is in A and X is in B. Okay? If you don't understand something, now or later, you can stop me directly. Okay? Don't wait too much. Okay, so the intersection of those two sets is here. It's the black thing here. That's the intersection. And the union is when you take both. So this thing plus this thing, like this. Okay, that's the union. Okay, there's another thing we have to define, which is the complementary. You have different notations in probability. Most people use a straight line over the letter. Some people prefer AC. That's the complementary set with respect to omega. Complementary set with respect to omega. That means that it's omega without A. Okay, so you have omega here. A is somewhere. And the complement is all outside A. Okay, so all outside A is here. This is A complementary. Okay. And finally, we need to define the symmetric difference. So maybe this one is new for you. Symmetric difference. Okay, the symmetric difference of A and B is something denoted by A delta B. And it's just the set A union B minus A intersection with B. So you have A, you have B, and you take the union without the intersection. That gives you this and this. Okay, the union without the intersection. Okay, that's all for the recaps on set theory. Okay. Yeah. If there's a very nice notation, I mean, it's simple. Okay, so this is notation. It's not very traditional in France, but it's very useful for more complicated probability. If B is a subset of A, okay, so you're in this situation, you have A and B is a subset of A, okay, we are going to use the notation A minus B, okay. This will means A intersection with B complementary. Okay, so what's the thing? It's just A set minus B. Okay, this is more used in France, but it's the same. Okay, you will see later why this notation is more useful. Okay, in particular, if we use this notation, the symmetric difference A delta B is just.
Sorry, sir.
Yeah.
A intersection B complementary is just B complementary.
In this case, yes.
Okay.
Yeah.
Thank you.
Yeah. Okay. Yeah. So that's all. Now, a new definition. It's very, very important. This definition. It's the indicator function. Indicator function. If you have a set A, so let's say is a subset of omega, the indicator function is a function denoted by one subset A, okay? You know, it's a bold one. It's the function from omega to 0, 1. And for any point x, it will return 1 if x is in omega and 0 if not. Okay, so this function tells you if a number x or if an element x of omega is inside A. Oh, sorry, I made a mistake here. This is not inside in omega, it's inside of A. This is A, this is A. Okay, so maybe we can make a simple plot, a 3D plot, wherever. So here you have A, sorry. Here you have A, okay? And the function 1A is the function that is equal to 1 if the points are in A and 0 outside. Okay, so outside this region, the function is 0 everywhere. Okay, this height is 1 and outside is 0. Okay, so the indicator function is a function that ask if a particular point x is or not inside of A. Okay. Well, that's very basic. This is in dimension 2. And of course, if you are in dimension 1, let's say you have a set here. This is A. Okay. This is A. Then the indicator function is 1 here and 0 outside. Okay, and the same thing in dimension 3 for n. Okay, well, that's very good. We are talking about probability, and probability stands for random phenomena. Okay, random phenomena, they are observed by the mean of experiments. Okay, you make an experiment, and that experiment will give you a value. For example, if you take a random people on the street and you ask for the age of the person, it's a random number. Okay, you can know in advance what's the value. It is not, you know, the person has a certain age, and the randomness, it's not on the age of that particular person. It's on the random person. You know, it's a very fine thing to separate. Randomness is not just something that we can not explain, but the thing I want to say is that people normally tend to misunderstand randomness. Okay, randomness doesn't mean chaos. Okay, randomness means just that we don't have a precise value to say at that moment, but that doesn't mean that the value is completely crazy. Okay, well, each experiment will result in an outcome. Okay, so here the vocabulary word you have to know in English is outcome. What's the translation of that in French?
Une issue.
Voilà, une issue. Okay, you make an experiment, you have an outcome, and this outcome is just a possible value of the sample space. The sample space or the universe is omega. Okay, and in machine learning, the word we prefer is sample space. Sample in French is échantillon. Okay, sample, échantillon. Okay, and an event, ou in French événement, is just a subset of omega. Subset, oops. So it's any subset of omega. Okay, let's give some examples. Example 1. If you toss a die, okay, the possible outcomes are 1, 2, 3, 4, 5, 6. Okay, you have a die here. Or wherever. Okay, and here the sample set is 1, 2, 3, 4, 5, 6. And a possible outcome, for example, omega is 2. Okay, that's a possible outcome. Okay, those outcomes can construct some events. For example, if you take the event of getting a multiple of 3, it's the subset 3, 6. Okay, this is an event. A is an event. Okay. That's a simple example. Maybe we can give another one. Example 2. Okay, if you are throwing a dart, okay, you have normally here some concentric things. I don't remember if it's red, white, or whatever. Okay, you have several radius of circles, and you want to know, for example, for this omega, which is the set of x, y in the plane. It's a circle, okay, the black one, such that x squared plus y squared is less than if the radius is r squared. Okay, and you can define a particular subset here. Let's say this region R. Okay, R inside of omega is a region of the plane, and it's an event. Okay, and you can give another examples. Next time we are going to make some computations on some exercises. Okay. Okay. We have to say, what does it mean that an outcome realize the event A? That's a definition. Maybe I can write it here. Okay. So we say that the outcome omega realize, that's the important word, realize, the event A, if omega is an element of A. Okay. For example, in the die case, number 3, omega equals 3, realize A, which have a multiple of 3. Okay. If we say that omega do not realize A, that means that it realize A complementary. Okay. And omega do not realize A if omega is in A complementary. Okay. Well, that's all. Now, two events can be incompatible. Events A and B are said to be incompatible if A intersection with B is empty. That means that you have here omega and A and B do not intersect A. Okay, so the intersection is empty, and we say in that case that the events are incompatible. Okay. Okay. We have a notation here. Okay, and it's just a notation which is useful. The notation is we say that the sum of sets AK to N. This is equals to the union for K equals 1 to N of AK if and only if, okay? Okay, so this is a notation. If we say it's a notation, we use column equal, okay? So when I wrote this, that means by definition. By definition. If the subsets AK are pairwise disjoint, if AI intersection with AJ is empty for any I different of J. Okay. So that means that I have omega here and a lot of AI, A1, A2, A3, etc., 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 AN. This notation with the sigma is used for the union only in the case that the subsets are pairwise disjoint. Okay. Okay. About that, is it clear for you?
Please, I don't understand. I don't understand very well what you said about the 2 point unequal, and I don't understand well. Please, this part.
You mean you don't understand why I use the sum?
Yes, I don't understand why you use this. Yes.
It's just a notation, okay? I mean the main okay, this term here, the union of AK, do you understand it?
Yes, I understand it.
Okay, so in the case that none of AI intersects another one, I can use the notation with the sum. Maybe I can say it in French. Si aucun des ensembles AI intersecte un autre AJ, c'est-à-dire s'ils sont tous disjoints, okay, dans ce cas, je peux utiliser, enfin, c'est ce que, quand je vais utiliser cette notation de somme, ça va signifier que c'est une union disjointe. Okay.
Okay.
C'est une union disjointe. In other books, you can find another type of notation, but for the same thing, which is actually not bad. It's the union square. You know, this is 90 degrees angle here. It's the union of AK for K equals 1 to N. It's another notation and it's the same. Okay. It's an union with straight lines. It's the same that this and it's the same that that. Okay. It's just a notation, but it means the union is performed over disjoint, mutual disjoint sets.
Okay. Okay.
Any other question? No? Okay. Now we are going to enter in the very new things. This is the next slide is the really new thing. Okay. Can you hear me? Yeah.
Yes.
Yes.
It came back.
Okay.
Yes.
So thanks. This is the very new thing. Sigma fields. Sigma fields. Okay. This is very new for you. Okay. Okay. So probability theory assign to each event a number between 0 and 1. That number is the probability of the event. Okay. And the collection F of the events to which a probability is assigned is not always identical to the collection of all subsets. Okay, that's very important. If you have a set omega, this is a very profound thing. Okay, if you have a set omega and you consider P of omega, the power set of omega, that means the set of all the possible subsets of omega, all the possible subsets of omega, well, you can't find the probability for any of those. That's important, okay? That means if A is an element of P of omega, we cannot always compute the probability of A. Okay, this is not easy. There are some events for you can't compute the probability. The fact that you can't compute the probability actually defines a property of the set. We say that the set is measurable. Okay, the key notion here is measurability. It is not true that any set can be measurable. Okay, for example, well, you know, for fractals and these kind of things, there are some examples of sets that can't be measured. Well, we will see that later, but just remind here that the idea is that we need to define a family, a smaller family here, which is, for example, in green, okay, sigma fields. Sigma fields will be a subfamily of those. It's not all the P of omega. It's just a subset of P of omega. Okay, that will be a sigma field. The sigma field is the set of events for which we can compute the probability. Okay, I will say it in French. Il n'y a pas tous les événements qui sont mesurables. Il n'y a pas tous les événements pour lesquels on peut calculer la probabilité. Puisqu'on ne peut pas, et on verra qu'on ne peut pas toujours, calculer la probabilité d'un événement, on est obligé de considérer uniquement les événements pour lesquels on peut mesurer leur taille, c'est-à-dire calculer leur probabilité. Et ça va être une sous-collection d'événements, c'est-à-dire quelque chose que P d'oméga, le power set d'oméga. Okay. We are going to define sigma fields. Okay. A sigma field will require the fact that every element is measurable. Okay, new definition then. This is the very first important definition you have to understand. Definition 1.
Please.
Yes.
So sigma field is the ensemble of element of set of omega that we cannot calculate the probability.
No, the opposite. It's the set of sets for which we can compute the probability.
Oh, okay.
Okay. So definition 1, let F be a collection of subsets, collection of subsets of omega. Okay, this phrase can be written more quickly as just F is a subset of P of omega. okay, is a subfamily of the set of all the sets of omega, such that number one, omega has to be in F. Okay, the universe is in F. That's the first requirement. Okay. The second requirement is that if A belongs to F, then the complement also belongs to F. Number two, if A is in F, then A complementary is also in F. Okay. And last requirement, number three, if A1, A2, AN, A1, A2, you have an infinite countable set of elements of F, okay, belong to F. Then, okay, the union of those elements belongs also to F. That means the union for k equals 1 to infinity of AK belongs to F. Okay. Okay, so that's the first definition of sigma field. Okay, so here this is the definition of sigma field. We say that F, if a sigma is a sigma field, if that. Okay. In French, sigma field has another name. The name of sigma field in French is tribu. Okay. Une tribu. On dit que A est une tribu si elle vérifie ces propriétés-là. Donc, si l'ensemble oméga est dans F, si pour tout ensemble A qui appartient à la tribu F, le complémentaire est aussi dans la tribu. Et si on a une suite infinie dénombrable d'éléments de la tribu, alors l'union est aussi un élément de la tribu. Okay. Do you have any question? Do you understand all the three all the 3 points on the definition?
Can you give us an example of which is a sigma field, an F which is a sigma field and an F which is not? So we can.
Yeah. Well, actually, you are going to try yourself to prove that the following thing is a sigma field. Okay.
Okay.
So I take F equals if I take omega and the empty set, is this a sigma field? Okay, question, is this a sigma field? Okay, so for example, I'm going to ask one of you. For example, Simon Chauvet, are you with us?
Yes.
Okay, can you please tell me, does this example F, which contains only omega and the empty set, is a sigma field? So you have to verify the 3 points. The first one, is omega inside F?
Yes.
Yes. Now, take any element of omega. Is the complementary set in F?
Yes.
Why?
Why? Because but we didn't define A, no?
Well, A is any of those elements. I mean, A can be this or A can be this. For example, if you take omega,
Yeah.
what's the complementary of omega?
Négative, comment on dit? Omega with the bar upper.
Yeah, what's omega bar?
Élément vide, enfin ensemble vide.
Yeah, the empty set.
Empty set.
And is the empty set in F?
Yeah.
Yeah. Now we take A equals the empty set. What's the complementary set of the empty set?
Omega.
Omega. And is omega inside F?
Yeah.
Yes. Okay, so point 1 is checked, point 2 is checked. Now, point number 3. If you take a collection of elements of F, in this case, we only have 2 of them. What's the union of F, of those elements?
The union is...
What's omega union the empty set?
The omega.
Omega, yes. And is omega in F?
Yes.
Yes. So point 3 is checked.
Okay.
Okay. This sigma field, okay, is in French you call this the tribu grossière. Okay. It's the more basic sigma field. It's not very useful because you have only 2 elements, but it's as an example of sigma field. Okay.
Sir,
I'm going to give you another example.
Sir, I don't understand something.
Yeah.
When you say that the complementary of omega is the empty set, I understand this equality, but not the second one. When you say that the complementary of the empty set is omega.
Yeah.
I don't like figure it to myself.
I don't know why. The complementary set of nothing is all. Non? Le complémentaire de rien, c'est tout.
But your omega can change like a lot.
It doesn't matter what's omega. Omega is the universe. It's the everything. I didn't took a particular example of omega. Does it make sense?
I just
Je vois pas.
I think.
Qu'est-ce que il te pose problème?
Je comprends que le contraire de tout, ce soit rien. Et voilà, c'est la première égalité. Mais sur la seconde, j'ai du mal à comprendre comment, à partir du rien, on arrive à mettre une égalité avec le tout.
Okay. Maybe a way to prove it is if you agree with this equality. If you take the complementary of A, and then you take again the complementary of the complementary, do you agree you have A?
Of course.
Okay. So if you agree that the complementary of everything is nothing, then the complementary of the complementary is omega, which is this.
Okay, thank you.
Okay. Okay, now exercise for you. Take omega equals A, B, C, D. A, B, C, and D. And you take F equals the empty set A, B, C, D, and omega. Please show that this is a sigma field. Okay, so write this into a paper, and then I can show you again the definition to verify. Okay, tell me when you're ready. Okay, you copied the exercise. Now I put you here the definition of sigma field, and please verify that it's a sigma field. Okay, and it will be okay. Let me check someone I do not know, and we will ask to Melissa to explain us why it's a sigma field. Okay.
Sorry, I'm very lost.
You're very lost, Melissa?
Yeah, very lost. I was just trying to understand why you write A apart from B, C, D. Or it's the same.
Sorry?
Why did you write A apart from B, C, D? Or it's the same?
No, it's not the same. It's apart. So here you have a, okay. Let me just make a drawing of this. Here is omega, okay? Omega contains A, B, C, and D. And I'm making a family that contains this potato, this potato here, omega, and the empty set, which can be defined. It's just an empty set somewhere here, okay? And I'm saying that if you take those 4 potatoes, it is a sigma field. That means that it satisfies these 3 requirements. The first one, omega has to be
F.
Okay. Then if you take a potato, a green potato, the complementary potato is also in the field, in the set of potatoes, in the green potatoes.
Yes.
And if you take any collection of potatoes, of green potatoes, the union is also inside this family F.
Yes.
Okay.
Yes.
Okay, try it for 5 minutes. I have to make a quickly call, and when I come back, you try to explain. It doesn't matter if you don't do the exercise well. It's just you have to try. Okay, give me just 5 minutes.
Can you go on the definition of? No,
yes.
Thanks.
So, sir? Excuse me, sir.
Je crois qu'il est parti pour 5 minutes.
Ah, ok.
Ouais, il a un call, donc il est parti.
Ça marche.
Mais vas-y, raconte.
Ouais, je sais pas, gros, en fait. J'ai l'impression que tu peux avoir que des nombres pairs en 7. En mode, tu peux avoir que 2 sets ou 4 sets et pas 3 sets ou 1 set, sinon ça valide pas la condition.
Bah, si tu en as un nombre impair, il manquera un complémentaire, forcément, non?
Ouais. C'est ça, ouais. Enfin, j'ai l'impression.
Après, c'est une condition nécessaire, mais pas suffisante.
En effet, un nombre pair, ce sera une condition nécessaire, mais c'est pas suffisant pour que ce soit un sigma field.
Ben, ça dépend après comment je définis ton oméga.
Non.
Tu peux en avoir 3 si oméga il contient le complémentaire de mon troisième.
J'ai pas compris là, par contre.
Non.
Là, par exemple, tu as pris un oméga avec ABCD. Si tu prends un oméga, par exemple, avec ABC, et tu définis ton F comme D. Enfin, alors, attends, il faut que je trouve un exemple.
Ouais, essaye de faire ce que tu viens de dire, tu verras que tu vas te retrouver dans le même cas. Tu vas avoir oméga, l'ensemble vide, puis A et BC.
Ouais.
Et si A et BC, c'est oméga?
Ouais, parce que pour qu'il soit complémentaire, il faut qu'il appartienne à oméga.
Et tu pourras pas mettre oméga et oméga à l'intérieur de ton...
Par exemple, regarde, c'est dans le F qui nous a donné un exemple.
Non, mais ce que je veux dire, c'est que si tu mets oméga, tu le mets qu'une fois. Tu peux pas compter 2 fois oméga ou 3 fois oméga.
Non, mais regarde, par exemple, là, enlève juste le A dans le F qui nous a donné. Genre, le A, il est inclus dans l'oméga déjà. Donc, on peut retrouver le complémentaire de BCD dans oméga.
Ça, je suis d'accord, mais oméga
Ah,
lui-même, c'est pas son
BCD
complémentaire.
dans oméga,
Oui.
c'est le petit A. C'est le singleton A. Non, je sais pas. Le oméga, c'est construit que de A et de BCD.
Oui, je suis
Plus
d'accord.
l'ensemble vide. Mais du coup, si tu dis complémentaire de A, c'est BCD. BCD, c'est dans... ça appartient au field.
Ton raisonnement, il fait que t'absorbes tout dans le oméga, en fait, au final. Tu te retrouves qu'avec oméga et l'ensemble vide.
Non, j'absorbe pas tout, mais en fait, là, c'est juste que, en gros, pour son field, ce qu'il fait, c'est qu'il décompose son oméga pour avoir tous les éléments qui composent son field. En gros, ça ne veut pas grandir là, ça veut pas dire grand-chose la phrase, mais en gros, c'est ça. Du coup, il a juste décomposé son oméga en A, B, C, D. Et après, pour son field, il a construit 4 éléments. L'ensemble vide, c'est l'identité, ça veut rien dire, ça sert à rien. Le A et après l'ensemble BCD. Mais du coup, le complémentaire de A, c'est BCD et le complémentaire de BCD, c'est A. Si tu regardes dans ses patates, c'est ça qu'il a fait. Et son ensemble vide, ça peut être n'importe où, comme ça peut être nulle part, vu que c'est rien. Et donc le tout construit oméga. Donc là, et après la petite 3, là, les 4 éléments, ils appartiennent au field, puisque leur union appartient au field. Non?
Moi, je suis d'accord avec ça.
Moi aussi, je suis d'accord.
Moi
Yes.
aussi.
Bien joué, Benjamin.
Putain, j'ai été convaincant, ça fait plaisir.
Pour une fois.
Ah putain. Et bon, on attend le retour du chef. Hein.
C'est toi le chef.
Oui, mais du deuxième.
Ah, ouais.
Moi, je suis délégué, je peux pas tout faire.
On pourrait faire prof, hein.
Et je donne un cours mi-semestre. J'ai hâte de vous avoir.
Ok.
Okay. So Melissa, are you ready?
Yeah,
Okay, so
sorry.
okay, so is omega in F?
Yes.
Yes, it's here. Now, second point, if you take any of those potatoes, is the complementary on F, okay? So for example, if I take the empty set, what's the complementary of the empty set?
Omega.
Yes, omega. And is omega in F?
Yes.
Yes. Now I take the second one. I take A. What's the complementary of A? You know, the complementary is all the other things. So if you, yeah, can you? The complementary is BCD. BCD. Okay, if I take apart A, all the rest is BCD. And is BCD in F?
Yes.
Yes. So this point is check. Now, if I take BCD, what's the complementary of BCD?
A.
A. And is A in F?
Yes.
Yes. Now, last one. I take omega. Everything. What's the complementary of everything?
Nothing.
Nothing. Okay. The empty set. And is the empty set in F?
Yes.
Yes. Okay. So any of those things, any A, any capital A in F, the complementary is also in F. So point number 2 is checked. Now, I have to take the union of all the things. Okay. What do I get if I take the union of empty field, union A, union BCD, union omega? What's the union of this?
F.
No. It's omega. The union is when you put all together. And when I put all the elements together, I get omega. I get ABCD. Okay. And the question is omega in F? Yes. So point number 3 is checked. Okay. So this family F is actually a sigma algebra. Okay. So that's another example of sigma algebra. Okay. And the idea is that, sorry?
Do you have another example, but where the condition 1 and 2 are validate, and the third one is not respected?
I didn't understand if it was a question or a remark.
No, it was a question. Can you show us an example where the third condition is not respected, but the first one and the second one are respected?
Yes. So you don't want the first one, and you want the 3 others. That's right.
No, the third one is not respected, but the first and the second is respected.
Yes.
Okay.
Exactly.
Okay. Yeah, sure. Okay, you take omega. Okay, that's the first one. And then you want something that the complementary is in F. Okay. So for example, if you take, let's say I take here A, B. Okay, here omega is ABC. A, B, C, D. And then I take the complementary so you don't want that the union is in F. If the union is not in F, okay, so I take A, B. The complementary has to be in F, but the union is not in F. So for example, here, the complementary, okay. The example will comes from infinite, for example, for segments of the line. If you take the interval I equals 1 over n minus 1 over n, 1 over n, okay, and you take F, the real line, okay, the complementary of I, okay, so if I is this thing, maybe in green like that, this is IN. The three are necessary, okay, so if you delete one of them, of course you can have examples of that situation. Okay, this is IN. Now the complementary is the thing, and the union has not to be in F. Let me think a little bit. But of course we can give examples for that because it's the three are necessary. So if A is, so you want 1 and 2, but not 3. Omega has to be in F, and all the complements are in F. Okay. And the union is, what does it means? Yeah, what does it means that the union is not in F? I have to construct it in that sense. What does it mean that this union is not in F? Is not in F. That means that if I take the complementary of that, because the complementary has to be in F, so that means that the complementary of the union is not in F, neither, because this is by 2. This is implied by 2. If, you know, it's the negation. So A implies B, the negation is A and non-B. That means that, okay, let me think. A implies B. The negation of A implies B is no B implies no A. So here, that means that if I take the union of the A case, which is not in F, by 2, the complementary is not in F, then the complementary is not in F. So that means that I'm looking for some, yeah, okay, so I was right here. And this is equals to, the complementary of the union is the intersection of the complementaries. So this is the intersection of all the complementaries for k equals 1 to n. It has to be not in F. Not in F, not in F. not enough. So I have to intersect everyone, and the complementary intersection is not enough. Okay. Let me think. Because I think, as far as I remember, I think we cannot find an example of that if A is finite. So if you want to take a counterexample of this, A has to be infinite, as far as I remember. So it's not, if you try to think in terms of A, B, C, D, I think it doesn't work, because here the tricky part is that you take an infinite countable sequence of AK, and you know here the union is infinity, and the tricky part becomes at infinity because the union can be outside of F. So I have to construct something that grows. Let me check quickly. I can find something on a counterexample of internet.
What about using the concept of limit?
Yeah, that's why the infinite part comes inside. Yeah, it's a limit thing. The case when it doesn't work, it's a n goes to infinity thing.
I mean, you just have to consider that your limit is not into your set.
Yeah, that's the thing we need. Okay, I think we have that. Okay, let me check. The union has to not be in F. The union is always increasing. And the complementary for a union which is increasing is decreasing. The union, something that gets smaller. What if I take, for example, I think this idea wasn't bad. Let me try again. Okay, I consider omega the interval minus 1, 1. Omega is the interval minus 1, 1 open, minus 1, 1 open. Okay, in the English notation, it's minus 1, 1. Okay, the open intervals are with parentheses instead of open brackets. This is the French, this is the English way of denoting that. Okay, I take that as omega. And then I consider the following interval. I say ik is, let's say, minus 1 plus 1 over k and 1 minus 1 over k. Okay, that means that I have ik here. Sorry, this is omega. Omega, it's minus 1, 1. Minus 1, 1. And then I take the sets which are in this form. Okay. The complementary has to be inside. What's the AK complementary? AK complementary is the set minus 1 minus 1 over k union 1 over k 1. Okay, if I want to construct a sigma algebra, all has to be inside, but the union has not to be in F. You find the counterexample, Alban?
I'm not sure.
Sorry, I don't
So you
understand
said
the
something.
definition of omega.
Omega is a set. There's no particular definition, it's just a set.
The first equality, the two equalities.
Omega, it's just the interval minus 1, 1. The interval minus 1, 1. Okay. Where did you send it? You sent it to me, huh? I don't know.
Yes.
I have to check. Example where union of increasing sigma algebra is not sigma algebra. Yeah, that's well. Okay, if F1 subset F2 are sigma algebras, what is one we're claiming is a sigma algebra? Okay. I don't know a counterexample of hand, but the problem with your argument, blah, blah, blah. You have the answer here. The problem arises in the countable union. Your argument is correct as far as it goes, but from the fact that union has to blah, blah, lies in the full union must be in one of the blah, blah. The explicit example is n. Okay, here we have an explicit example. Thanks to Alban. Alors, oops, it crashed, sorry. Share my screen, share. Okay, let's try to analyze this example. So it says, take omega equals to the natural numbers, omega equals n, and let Fn be the sigma algebra consisting of all the subsets of 1n and their complements in X. Okay, so they say F is the set of the things that are 1, 2, until n, for n in n, union, the complements. So the complements is the set of n's to infinity for n in n. Okay, so you take the numbers from 1 to n, and the complementary is the list of infinite numbers from n plus 1 to infinity. Now let xi be 2i. So they say xi equals 2i. Then each xi is in the union of f. So if you consider the union of fi, okay. Okay, so this is fn. Fn, now they say, let xi equals 2i, then each ai is in this union. Xi is in the union, but the union does not lie in any of the fk. Okay, but the union of ai, of fi, sorry, it's not in any fk for any k. Hence, it does not lie in the infinite union of Fk. Okay, let's try to analyze this example that proposes Albin. So we have omega, it's the natural numbers. Fn is a sigma algebra. Xi is this. Xi is in any of the Fi's. Yeah, because if you take x3, you have the number 6. And 6 is, of course, in the union of Fi. Because why it's why is 6 inside those?
Actually, you can find a k for any I, but you can't find an I for any k.
Yeah, I'm trying to understand this part here. I think it's not true, no? Because, for example, if you take I equals 3, for I equals 3, you have x3 is the set containing 6. But 6 is not in this union. Tu vois, le nombre 6 n'est pas dans les unions. Tu vois, ces ensembles-là, c'est des unions de 1, 2, 3, 4, 5, 6, par exemple, avec 7, 8, 9, 10 jusqu'à l'infini. Mais ce sont des blocs longs comme ça. Et à aucun endroit, tu as juste des blocs. En fait, je pense plutôt que ce qu'il voulait dire ici... Ah non, excuse-moi, je me suis trompé. Non, non, si c'est ça. Then each xi is in the union of fi.
Après, monsieur, est-ce que c'est vraiment important? Parce que sinon, vous pouvez nous apporter la réponse au prochain cours.
Bah, c'est important dans le sens où les mathématiques doivent être transparentes et limpides. Et parce que pour comprendre les définitions, pourquoi elles sont comme ça et pas moins restrictives, il faut dire que chaque point est essentiel. Et pour dire que chaque point est essentiel, il faut montrer des contre-exemples qui disent bah, si on n'a pas ce point, on aurait pu alléger la définition. Donc ça, c'est...
Can you show me the difference between omega and Fn? Because it's massive, for me, it's the same. It's the same.
Omega, I mean, in this example of in general?
In general. Omega, no, in this example.
In this example, well, omega is the natural numbers. This is 1, 2, 3 until infinity.
Yes.
Okay. And this is, so this is 1 potato, and this is 2 potatoes. This one is this one, and this one is this one.
But
and it's different from that.
But the union of the two is not given omega?
Yes, the union of both is omega, but it's not omega. You know, it's like, say, yeah, here I have 2 books. And the union of the 2 books are the 2 books. But the 2 books, you know?
Yes, okay, I see.
It's the structure that it's important. Okay, yeah, maybe we can continue. Actually, who asked the question? I don't remember.
It's me.
Okay, so Simon, for the next lecture, try to bring us a counterexample, okay? Yeah, it's a very classical thing. I mean, you can find normally in any measure theory book. Normally they are, okay, you look for measure theory. or Albin also can bring us the counterexample if you find it. This one, I think it's not exactly the counterexample for the question Simon asked. It's more why the union of sigma algebras is not a sigma algebra. It's something else. Okay, so that was the sigma algebra. Okay, now the next thing is probability of events. Okay, probability of events. Okay. So this is a definition. Definition number 2. What's a probability? A probability on a measurable space omega f. So what's a measurable space? Is nothing difficult. Oh, sorry, my computer is getting out of power. Yeah. So what's a measurable space? Is just a couple of a set omega and a sigma algebra f. Okay. Donc, un ensemble mesurable, c'est une paire où il y a oméga, un ensemble, et f, une tribu. Okay, that's a measurable space, the couple omega f. And we say that a probability on omega f, okay, is a function, is a map, okay, is a function p that goes from f to the real numbers such that number 1, for any a, the probability of a is a number between 0 and 1 for any a in f. Okay, that's the first requirement. Requirement number 2, the probability of omega is equals to 1. And the requirement number 2, the probability of disjoint union of sets, which is the sum of ak for k equals 1 to infinity, is actually just the sum of the probability of every subset ak for k equals 1 to infinity. Okay, that's the third requirement, and this has to be verified or satisfied for all sequences ak, k bigger or equals than 1, and ak intersection of aj empty. Okay, so this third relation has to be satisfied for any sequence of pairwise disjoint events in F. This third requirement has a name, okay? Is the sigma additivity property, okay? I don't know why I have problems with my, okay? So this third thing is the sigma additivity property, okay? The third one has can be written in a simple way, okay? For two events. If you have omega here and you have two disjoint events, A and B, well, the sigma additivity property says that the probability of A union B, so the union is disjoint, is just the probability of A plus the probability of B. Okay, that's the sigma additivity in the case of just two events, but the third property requires that for general sequences of events. Do you have any question?
I have a question about the notation. For the point 3, it is not the probability of the union of the element.
Yes, it is. It is. If you remember, we say that this notation sigma, just for recall, we say that sigma AK, it was the union of AK if AK was empty intersection with K for any J different of K. It was a notation, okay? So when I say sum of events is the union of events, but additionally I say that the events are disjoint, pairwise disjoint.
Okay.
Okay. Okay. Any other question about that? No? Okay, so today we saw two main definitions. The first one is what's a sigma field or sigma algebra. You can find on the internet both names, sigma algebra or sigma field. In French, the word is tribu. Then why it's important to say to have sigma fields, it is because only the elements of the sigma fields will be the events for which we can compute the probability. Okay. Now, what's a probability? A probability is a function that goes from f, which is the sigma field defined on omega, to the real numbers, that for any event A, it returns a number between 0 and 1. The probability of the universe of omega is 1. We say that omega is the certain event. And the last and certainly most characteristic property is the sigma additivity. That means that the probability of disjoint events is just the sum of the probabilities. Okay? Well, that was new for you, the sigma additivity property. Okay. Next time, if we are, I don't know, normally if we are not confined for next week, normally we will see on at school, okay, and you will have a set of exercises to do that take into account all the things we learned today. Okay. Okay.
Sorry.
Yes.
Just about the definition, just before, a probability should go from F to R plus, no?
Well, yes, actually it goes to 0, 1, but that's property number 1. You know, the point number 1.
Yes,
it goes not to R, the whole R, it goes to 0, 1.
Okay.
Okay. Now, some basic formulas. Some of them you know them, other maybe not. So theorem number 1, for any event A, in F, the probability of A complementary is 1 minus the probability of A. Very basic thing. Okay, the probability of the empty set then is the probability of omega complementary, and this is 1 minus 1, and this is 0. Okay, so the probability of and the empty set is 0. Now, number 3, the probability is a monotone function. Okay, it's a increasing function. That means that if A is included on B, okay, if A is a subset of B, then the probability of A is smaller than the probability of B. Okay, so this is the definition of an increasing function. P is a function, and here it's increasing on subsets. If A is smaller than B, the probability, which is the size of the set, is smaller. Okay, so if this is A and this is B, A is less probable than B. Okay, we can actually prove that last thing. It's very easy to prove. Okay, you have to say that B, okay, can be written as A plus B minus A. Okay, do you agree with that? And then if you compute the probability of B, this is the probability of that thing. And since those are disjoint sets, it's just the probability of A plus the probability of B, because of the sigma additivity property. And this is a number between 0 and 1, and this is a number between 0 and 1. That means that this thing is actually bigger than P of A, because you add, you add P of A plus something, and it has to be bigger than P of A. Here you have P of A, here you have P of A. If you add something, it's bigger. Okay, so that's the proof of P of B bigger than P of A. Okay. We have the sub-sigma additivity. That's also a consequence. It's the same thing, but in the general case. Okay. In the general case, you can say that the probability of the union of AK for k equals 1 to infinity is smaller than the sum of the probability of AK for k equals 1 to infinity. It's the generalization of the thing before. This is the sub-sigma additivity. Sub-sigma additivity. Okay, this is the general case. For example, you take A here and B here. The probability of the union is this, is smaller than the probability of A plus the probability of B. Why? Because here I have an intersection, so it's I have to take that into account. Okay? Hein? C'est juste parce que comme il y a l'intersection, la probabilité de l'union va être plus petite que si j'additionne séparément les probabilités de A et la probabilité de B. Okay. Well, now we have another theorem which is important. Okay, those were properties. Now this is theorem that says that let an n bigger than 1 be a increasing sequence of events. What does it mean that it's an increasing sequence of events? That means that an is included on an plus 1. Okay, so you have things like this. Okay, an plus 1 is bigger. Then the probability of the union for n equals 1 to infinity is actually the limit when n goes increasingly to infinity. This is a new notation for you. I think you never saw it in math, but it's very common. N tends to infinity by increasing values of the probability of an. Okay, we can understand that very easily. If you have increasing subsets, every an is included on the an before, then the probability of the infinite union of the events will be just the limit of the last probability. You compute just the probability of the last one, and you make n goes to infinity. Okay. You can have a corollary from this. Okay. If you take the intersection, what's the intersection of those? Okay. Well, it's the limit of the same thing. Just okay. It's easy if I write it. Corollary. Everyone knows what a corollary is. A corollary is a simple result deduced from a theorem. Okay, so from my first theorem, the theorem just before, I can deduce that if Bn is a decreasing sequence of events, if it's a decreasing sequence of events, what does it mean? That means that B of n plus 1 is included on Bn, is included on Bn, okay? Then the probability of the intersection for n goes to 1 to infinity of Bk is actually equals to the limit when n goes to infinity of the probability of Bn. Okay, so in this case, you have the opposite thing. You have Bn plus 1, which is smaller. And if you want the probability of the intersection, well, it's just the smaller one when you take n goes to infinity. Okay. Any questions about that?
Not for me, it's all clear.
Okay. Okay. Now, a definition about negligible sets or negligible events. Negligible events are those events that have zero probability. Okay. So definition. A set n inside of omega is called P negligible if the probability of that event is 0. Okay, so the negligible events are those that have probability 0. In French, you say négligeable. Donc les événements négligeables, ce sont ceux dont la mesure, c'est-à-dire la probabilité, est nulle. Okay, and here also you have a very important example. Let's say here you have omega. And we say that the probability of A is the size of A with respect to omega. Okay, let me ask Oriane, for example. Can you please, Oriane, tell me if I take this n here, what's the size of n?
Like the dimension.
Yeah.
1.
The dimension is 1, and this straight line, this green straight line, does not have a surface, okay? Yeah. It's just a line. So the surface of the line is 0. That's an example of negligible event, okay? If you are in 3D, for example, okay, let's say we go to dimension 3. In dimension 3, you can consider this potato, A. And this potato has a volume, okay? But in dimension 3, if you consider a plane like this, a plane does not have a volume, okay? So the plane will be a negligible set for the measure in 3D, okay? This set is negligible because it doesn't have a volume, okay? And that's the general thing. If you are in dimension n, objects of dimension smaller have 0 measure, okay? The plane has 0 measure here, but also if I consider a straight line, and also if I consider a point, all those 3 have 0 measure, okay? That means that what's the probability if I launch a point inside that 3D space? What's the probability to go into the plane n? It's 0, okay? 0 probability to be there. Is it clear? Okay.
Yes.
Now, if you consider the union of negligible sets, it will remain a negligible set, okay? That's a theorem. A countable union of negligible set is negligible. If you take this plane and that point and that line, okay, and you consider the union of those 3, then it's also a negligible set. It doesn't have a volume, okay? And here the word countable is important, okay? It's more or less the same thing, the same debate we have at the beginning with respect to the third condition of sigma field. When you go to an infinite number of things, okay, then strange things can happen. If you take an infinite number of planes, but not a countable infinite number of planes, but a non-countable number of planes, then you can construct a volume, okay? It's an important thing. The infinity part is the tricky part. Okay, now we can talk about independence and conditioning, okay? Maybe someone can tell me some souvenirs of the precedent years about probability. For example, Julia Beroux. Okay, are you there, Julia?
Yes.
Can you please tell me what does it mean that 2 events are independent? Qu'est-ce que ça veut dire que 2 événements sont indépendants?
Yeah, okay. There is no consequence in those events.
Mm-hmm. Yeah, more or less. For example, or can you give us an example of 2 independent events?
Well, you can. Well, I think when you throw a dice, it doesn't affect the second time you're going to throw it.
For example, if I consider a dice and I consider two events, for example, event A is getting an odd number, and event B is getting a even number. Okay, odd numbers and even numbers, nombre pair, nombre impair. Are those events independent?
Well, I think yes, because if the first, if you, well, I think it's independent because the fact that obtaining an odd number doesn't affect, doesn't mean you're going to have an even number after it.
Well, actually, they are not independent. Okay, the independence it's a very important notion in probability, and it says that two events are independent if knowing something about one of them doesn't give you any useful information about the other one. Okay, and it's not the case with even numbers and odd numbers. Why? Because if I know that my result is an even number, then automatically it's excluded that it can be an odd number. Okay, so the definition here comes from conditional probability. We will say that, so this is a definition. We say that A and B are independent. Okay, A and B are independent events, if the probability of knowing, the probability of A knowing that B has been realized is equals to the probability of A. Okay, here we use the conditional probability. This is the conditional probability. C'est la probabilité conditionnelle d'obtenir A sachant que B est réalisé. So you know that B has been realized, and you want to know that, and you want to compute the probability of A knowing that B has realized. And if this probability, so if this information about B doesn't give you anything, that means that that probability is the probability of A. Okay, this is the conditional probability, and we conditional probability, and most of the machine learning things in math use conditional probability and Bayesian things and Bayes theorem, okay, that asserts some things on Bayes theorems, and those are defined in terms of conditional probabilities. Okay, so what's the conditional probability? You have an event here, which is omega, and you have two events, A and B. And you want to compute, sorry, A and B. And you want to compute the probability of falling in A, but you already have an information. You already know that you are in B, okay? So if you know that you are in B, then it is not true. Well, no, it is not true. No, it's not the word. It's you already have some information about your potential location in A. You are in B, so you can't be everywhere in A. Okay. if you know that you are in B, the only place in A that you can fall is here. And this site is the intersection of A and B. So the probability of A knowing that we are in B is the probability of the intersection, okay? Because I have to measure what's the intersection of A and B. And now it's not with respect to the size of omega, because I know I am in B. So it's respect with B. So this is divided by the probability of B. Okay? That's the definition of this probability. Okay? Is the idea clear? The probability of A given B, the probability of A given B is the probability of the intersection divided by the probability of the event with respect I am conditioning the computation. Okay, let's make a computation then. Okay, imagine, okay, we are going to ask that to Lucas Chenel. Okay. Okay, so Lucas, let's say that omega is the possible results of a dice 1, 2, 3, 4, 5, 6, and A is having, I don't know, number 2, 4, 6. Okay, this is A, and B is just the, I don't know, the multiples of 3. Can you please tell me what's the probability of A given B? So you already know that you are in B. So you can be 3 or 6.
Du coup, on a la probabilité de l'intersection qui vaut 6.
Non. La probabilité, c'est un nombre entre 0 et 1. Elle ne peut pas valoir 6.
Ah oui, oui.
C'est quoi l'intersection de A et B? C'est quoi l'intersection de A et B? C'est l'ensemble qui contient 6. Maintenant, quelle est la taille de cet ensemble? Quelle est la probabilité de 6?
Un sixième.
Un sixième. Ok, donc ça c'est un sixième divisé par la probabilité de B. C'est quoi la probabilité de B? 2 sixièmes. Et ça fait 1 sixième sur 2 sixièmes, ça fait 1 demi. Ouais?
Oui.
Pardon, 1 sixième fois 2 sixièmes divisé par 2 sixièmes. Ouais, c'est ça. Ça fait 1 demi. OK? Though, is it clear for everyone, this computation? So the probability of A knowing B, okay, is the probability of the intersection. Here the intersection is just the number 6, the set containing number 6. The probability of that event is 1 over 6. And then the probability of B is 2 over 6. And when you simplify that fraction, you get 1/2. Okay?
Okay.
Now, if we come back to the definition of independence, we say that two events are independent if the conditional probability of A given B is equals to the probability of A. And we just define what was this probability. So this is the probability of A intersected with B divided by the probability of B. Okay. So this quantity is equals to this quantity. That implies that we have an equivalent way of verifying that two events are independent. Two events are independent if and only if the probability of the intersection is the product of their probabilities. This was the way you saw independence at high school. Okay. The probability of the intersection is the product of the probabilities of each event. Okay. Now, if we come back to the example we asked to Julia, we have an event which is odd numbers, even numbers. So here this is omega 1, 2, 3, 4, 5, 6. We have A, which is this set, and we have B, maybe in red, which is this set. Okay, and we ask to Julia, are those events independent? A independent of B? Well, to know if they are independent, we have to compute the probability of A given B. And the question here is this equal to the probability of A? So please, Julia, what's the probability of A in this case?
Well, it's 1/2.
1/2, 1/2.
1/2.
Now, the probability of A given B, by definition, is the probability of A intersected with B divided by P of B. What's the intersection of A and B?
Nothing.
Empty. It's the empty set. Okay. And what's the probability of the empty set?
0.
0. And here you can see that on the left-hand side we find 0, and on the right-hand side we find 1/2. And of course, those two numbers are not the same. So it is not true that A and B are independent. Okay, so you can see that it's not because the sets are disjoint, it is not because the intersection is empty, that this implies that they are independent. Okay, independence and disjointness are different properties. Okay, any other question? No? Okay. So that was independence for two events. Two events are independent if the conditional probability of one given the other is the probability of 1. Okay, of A. Okay, what happens if I have a set of events? Well, how to verify that those events are independent? Well, we have a practical way to verify that n events are independent. So we will say that A1, A2 are independent if the probability of the intersection of all those events, of the intersection of AK for k equals 1 to n, okay, is equals to the product for k equals 1 to n of the probability of AK. Okay, it's nothing complicated, it's just the translation of this property here at the end. Where's my here? This property is an equivalent way of verifying the independence of two events. Two events are independent if the conditional probability is equals to the probability, And by definition of the conditional probability, I can rewrite this equation as P of A intersection with B is just the product of the probabilities, okay? The last blue thing here generalized to n events. So if you have n events, the probability of the intersection is equals to the product of the probabilities. Okay. Now we can give an example here, very basic example. Let's say omega is again the result of a dice, 1, 2, 3, 4, 5, 6. And we say that A equals 1, 2, 3, B equals 3, 4, 5, and C equals 5, 6. Okay. Please, maybe, I don't know, Thibault Lejoux, can you hear me?
Yes.
Okay, can you please tell us, are those three events independent? Okay, so if what are the things we have to verify if we want to know if they are independent? We want to compute the probability of A intersected with B intersected with C. The question is this equal, it's a question, to the probability of A? I'm sorry about my writing. I know I wrote very bad.
No, it's not independent.
Yeah, it's not independent. Why?
Because the first one equal to 0.
Yeah, because the intersection of A, B, and C is the empty set, and the probability of the empty set is 0. So we have a 0 on the left, and on the right we have something which is different from 0. Okay, it's different from 0 because A, B, and C, the probability is 1/2, 1/2, 1/2, and 1/3. Okay, so this is A, then B. I don't know why this thing goes out. I'm sorry about that. Okay, A is that thing, B was that thing, and C was that thing. Okay, those three events are not independent. Okay. Okay. Next time you will do a lot of exercises on this, but I have to continue. Okay. Now, Bayes calculus, Bayes formula. Okay. Bayes calculus. Okay. Okay. We have a theorem, which is the Bayes rule of retrodiction. And that it says the following thing: the probability of B given A, okay, so I turn the things, the probability of B given A is equals to the probability of A given B times the probability of B divided by the probability of A. Okay, that's as long as we do not divide by 0, that means that P of A is positive. Okay, this is the Bayes formula. It's a very profound formula. The proof is very simple, but it's a profound thing. So the probability of B given A. Okay, so it's the other one. It's the symmetric condition. It's just the probability of A given B times probability of B divided by probability of A. You can rewrite this equation in another form. You can say it's the probability of B divided by A, B given B, sorry, B given A is divided by the probability of A given B is the probability of B divided by the probability of A, okay? And B on the top, A on the top. The first one is on the row, okay? It's an equivalent form. And why it's important? Well, because sometimes you have an information about this conditional probability, but the thing that you really want is the other one, okay? So the Bayes formula gives you a way to estimate the other probability knowing the conditional one, okay? I will give you an example. Imagine you go to doctor, okay? And you have some rash. And the doctor says to you, 90% of people that have smallpox, you know what smallpox is in French?
No.
It's the variole, la variole, okay? So it's a disease, an infectious disease. Okay, so you go to the doctor and you have this rash on your face, and you are quite afraid because it looks like the smallpox, and the doctor says to you, 90% of people that have your rash, sorry, 90% of people that has smallpox have your rash, okay? But this is not an important information for you. You don't want to know that people that have actually the disease present that symptom. The really thing you want to know is what's the probability you have smallpox given you have a rash, you know? And if you compute that thing, the probability is very low, okay? So on the next today, you will do a lot of exercises with respect to that, but today I want to introduce that formula, okay? This formula, you have to know it without any doubt, okay? It's a formula you have to learn today, okay? Any question about that formula? Let's prove the formula, okay? The proof is very simple. So you take the conditional probability. You say probability of A given B. By definition, we say that this was probability of A intersected with B divided by the probability of B. Now, if I turn this into the symmetric conditional probability, probability of B given A is the probability of A intersected with B divided by the probability of A, okay? Now, you are going to replace this intersection here. If you replace this intersection with those two parts, okay, you get that the probability of A given B is nothing more than the probability of B given A times the probability of A divided by the probability of B. And that's the proof of Bayes formula, okay? That's all. And again, all the formulas we saw today, they have a simple example with two events, but they generalize to a sequence of events, A1, A2, AN. Okay, and we can just write the general formula using the same idea. So the final formula is this theorem. Okay, if B1, B2, Bn are events that forms a partition of omega, if B1, B2, Bn are events that forms a partition of omega. What does it mean that it's a partition of omega? It means that they are disjoint, okay? And if I collect all the sets, I get omega, Bn. Okay, that's a partition of omega. Then for any event A, here I have A, okay? Then for any event A in the sigma algebra of omega, we have that the probability of A is the sum of the probability of A given Pi times the probability of Pi. And this is a sum from 1 to n. Okay? This formula is known as the total causes formula. In French, is la formule des probabilités totales. And it says that the probability of A is, look at the drawing, okay? The probability of A is the size of A. Well, the size of A is the sum of this little piece plus little piece plus this little piece plus this little piece plus this little piece. And what are those little pieces? It's just the probability of falling in A given that I am in Bi, okay, proportionally to the size of Bi. Okay? Donc, la formule des probabilités totales dit que la probabilité de A, hein, de tomber dans A, bah, c'est juste la somme des morceaux qui composent A lorsque je la décompose sur les BI. C'est le morceau qui est dans B1 plus le morceau de A qui est dans B2 plus le morceau de A qui est dans BN. Okay? That's all. Okay? The proof can be it's straightforward. Okay? The proof, well, if you want, try to do the proof, and if you need something, you can come next time and ask me something. Okay? Any question about that? We have 7 minutes more. Okay. Maybe we can stop here now. Please, can you please tell me something more about yourself? Okay, those who were in Montpellier last year, I know you already. Can you please turn on your cameras now? Thanks. Okay, so you weren't in Montpellier last year. Okay, so for those who wasn't in Montpellier here, I guess you were in Troyes. Who was from Troyes?
Me.
Who is me? Ah, okay. Tian Yuan, you are from Troyes.
Yes.
And let me put you all together. Okay, and who else was from Troyes?
And me.
Me.
So cool.
Okay. And who was from So?
Me.
Me.
Okay, perfect. And is someone else from another part of, maybe an exchange student or something? No? Okay. Anyone? Or you say something?
Elisa.
Ah, okay. Where are you from?
Colombia.
And which university?
AI University. It's another school of engineers.
Okay. And right now you are in Colombia or you are in France?
In France, in Montpellier.
Okay, in Montpellier. Perfect. So I hope for you all that you are new in Montpellier, you will enjoy the city. And I hope it was not too fast. If it's too fast, please just stop me, ask questions, and try to verify next time that you understood everything we saw today. Okay, so your homework is see again the video if necessary. Try to understand everything we did today, and if you have questions, next time you ask me. Okay, and next time you will have a list of exercises to do during the lecture, and hopefully we will be together, but probably not. Okay, probably will be in confinement for that moment. Okay, so have a nice day. See you next time and work well.
Thank you.
You too.
Thank you.
Bye.
Bye.
Thanks.
Bye. Thank you.
Bye.
Goodbye.
Goodbye.